So after you design the hardware and implement it using HDL, and before you actually jump into writing an application to utilize that hardware, we have decided to adopt the method of writing device drivers that actually will abstract the hardware ideas from the application layers. And the purpose again of the device drivers is to encapsulate certain information about the hardware and make the application developers' life a little bit easier by not needing to understand what the hardware level or what's the hardware and how the hardware is designed. So what you're going to see is that for every I/O module you actually instantiate in hardware, you're going to have to associate it with some sort of a driver in the middle that actually translates the hardware and the requests from the application into hardware commands. So the way we're going to implement these drivers is as simply as C++ classes. And the reason why we use C++ classes because they're pretty convenient in encapsulating data, and it's a very convenient and comfortable data structure to actually use. So what we're going to be using, for example, if we instantiate a UART core, we're going to actually include a driver for it, and that driver is just basically a class. And not only do we write a class for it, but whenever you actually write the application program, you're going to have to create an instance of that class, and of course the constructor will initialize all the necessary things and so forth. So let's jump into looking at examples of these drivers to see how they actually are written. And we're going to start with the general purpose output and the general purpose input. So these are very, very similar. So you're going to see me writing them in the same file system. But anyway, so we get started this way. The first thing that you need to know is in C and C++, usually we have some sort of a structure in terms of implementation, in terms of interface. So we're going to split our implementation of the driver into two different things. The first one is actually implement the interface with the user. So as an application developer, what you do is you say include, and you include some sort of a file that actually ends with the .h, and that's what we call a header file. And it's called an interface file because it contains information as an application developer that tells you what that driver does, but it doesn't tell you how it is. The next implementation is actually in here, which is the second file at the bottom in here. And you create a separate file and you put all the implementation in it, and that file usually ends with CPP or .c, depending on whether you're writing C or C++. We're going to write C++ because we're dealing with classes in here. We're not going to utilize a lot of C++ functionalities because sometimes it takes a lot of memory, and C is a little bit simpler. But for drivers, we're just going to use classes, so we'll have to use C++ for that matter. So the code you see in here is actually split into two files. The one is gpio._h, and as you can see, it's .h because this is the interface, and this one here is the implementation. So let me go into details of what's an interface and what's an implementation. So in an interface, you're going to see the general purpose I/O. The first thing it does, and this is a good template for all the drivers we're going to see, that it actually enumerates the register map. And if you remember, an I/O usually contains a bunch of registers. Each one of them is 32 bits. Okay, it's actually exactly 32 registers. Each one of them is 32-bit. But we need to have some sort of a map to figure out what these registers mean for each one of the drivers. So this particular driver, which is a general purpose output, as it turns out, that it only utilizes the very first register in it, because as you probably remember, a general purpose output is connected to the LEDs, and it only actually output. You just need half a register. Actually, you don't even need all of the register. You just need the first half of the register because you only have 16 LEDs on that board that we're utilizing. But anyway, the register map in here, its purpose is to tell me, well, I have a data register and its offset is 0. So it's basically just tell me this is the only map we have. More drivers or more complicated drivers will have a little bit more information in this section, which is the register map. Next, as any other class, you have to have a constructor and destructor. So the constructor, you're going to see its purpose is to initialize the I/O appropriately. Certain I/Os need certain resets, signals and whatnot. In this particular case, you're going to see that there isn't a lot. It's just a general purpose output. So the implementation would be just basically just store the base address of that particular I/O. Remember, it's like the base address is where we have placed that particular I/O, and it's important. So we're going to pass it to the constructor. Okay, and then here's where the meat of any driver is actually the methods that it can carry out, basically the class method. So in here I see a couple of functions or a couple of methods. One is called a write and the other one is called another write. So it's basically an overloaded function. And as the name implies, you're writing into the output that basically this is what you're displaying to the LEDs. The differences between both, if you actually, you can read the comments usually, or you can actually take a look at its input. So the input in here is a data that is 32-bit. So technically you're writing all of the LEDs or all of the output together in one shot, as opposed to the next one is actually, it takes a couple of inputs in here or a couple of parameters, and these parameters are basically the bit value, basically whether you want it 0 or 1, and the bit position. So technically, let's assume that you have passed 1 and you have passed 2. That means you tell me that the output number 2 should be set to 1. Basically, you're turning on the second LED, the third LED, well, LED number 2. Okay, and as any other good class design, you're going to see that we have some private members in here, and in this particular case, the private members actually stores the base address of the module, which is the general purpose output in here, and the other thing is actually stores whatever you send to the LEDs, because once you send it to the output, you can't read it back, generally speaking. You can't read the value of an LED, so we're going to just keep it here just for the sake of tracking. Okay, and that's the interface, and that's why we call it an interface, because as an application developer, this is all you need to know to use that particular driver to use a general purpose output. So you're going to see if you're writing an application that utilizes these LEDs, all you have to do is create a class or create an instance of this class and then call its sub methods in here, passing it certain data, and you're going to see that you'll be basically turning on the LEDs, and that's it. Now, how are these implemented? Well, you're going to have to look at the implementation file, which is the .cpp. It's abstracted from the application developer, but if you are designing this because you're the driver developer, because you're actually driving these, you need to understand the hardware so you can actually write these functions correctly. And the implementation is pretty simple. So the constructor is basically telling me, hey, take the core base address that you passed me through a constructor and just save it in my private my private member in here. And the next one is the right data. Basically, the data that is on the LEDs, initially it's going to be 0. So I'm going to basically turn all of them off. So this is why I said it initializes the module. In this particular case, the initialization is pretty simple. Let's initialize it to 0. Like the destructor is actually not usually used, because once we create an instance, basically we created a driver. We're not going to remove the driver as long as we're going to be using it, unless like that driver is not necessary, then you're going to have to take the hardware off as well. And then you're going to see that the write function is pretty simple. Or all it does, it's going to take some sort of a data that is 32-bit. It's going to store it in that write data that we have, and then it's just going to call that macro we have seen previously that provides the base address, which we have, and it provides the data register, which basically we have as 0 because I know it's the offset, and then write data. The other write, which is overloaded, you're going to see it's extremely similar. It uses these C-bit operators in here that tells me like, hey, the write data, you're going to have to change that bit position to bit value, whatever it is, and then you're going to rewrite the whole write data again. You can definitely issue a write, but anyway, you can actually, there are many ways to implement it, but this is one way to do it. Okay, so let's jump to the general purpose input. It's pretty much the same exact thing, and you're going to see that the register map is 0, and I have a constructor destructor. Here's the meat of the driver, and the meat of the driver is basically you reading. Remember, general purpose input is connected to switches in our cases, so you can either read all the switches together, or you can see that I have an overloaded function or method that tells me you can read a specific bit position, basically a very specific switch. Again, as an application developer, this is what matters to you, because you understand now how you can actually read all switches of one switch alone. You don't care about how it's implemented. But as an application, as a driver developer, you're going to actually go and implement these, and you're going to read it. They're pretty similar to the write position or the GP output, which is the write. And here I'm using IO read instead, and I'm using pretty much the same exact methodology. Okay, again, like I didn't talk a lot about the register map in here because it's very similar to the general purpose output. It's just basically I have 32-bit registers, and all I care about is actually the very first one. And again, I only care about the very first 16 one of them because I only have 16 switches on my board, but we're gonna just read all 32-bit and whatnot. So because of the similarities of these general purpose input and general purpose output files, you're going to see that I am providing you with files that have the drivers for both of them together in the same file. Generally speaking, each module, each IO module will have completely separate file, but these, because they're pretty short and pretty simple and they're pretty useful, and we're going to include them all the time, we're just going to have them in here, okay, in the same file. So we move on to a little bit more complicated driver, and that driver is actually for the timer module. So the timer module, as you probably remember, it's actually its purpose to keep track of system time. And you're going to see later that basically the minute you operate the system, it's going to turn on, and I do have a timer. So taking a look at this, I'm just providing you the .h. This is the interface. As an application developer, this is what matters to you. If you don't care about how it's implemented, you don't understand the hardware. So let's take a look at that. So you're going to see that I have a register map, and this register map is a little bit more complicated. Usually it comes from the hardware developer in collaboration with the driver developer. They decide what to do. So again, I usually have access to 32-bit register. Each one of them is 32-bit. This register map tells me that I'm utilizing the very first register here as a counter lower word, and the second one as a counter upper word. Okay, and frankly speaking, this is a little bit of an error in here. It should be here. Actually, this is what we care about at up to 16, because the way that the hardware is implemented, you're going to see later that the timer is actually not. It's actually 32-bit plus 16, which is 40. I believe 48. So 48 bits. So you only need one register and a half from here. So you can see that the register map tells me the counter low word is 0. That's the offset for it. The upper register basically is that. And the comments is actually telling you that it's only 16 bits. That's what we care about. But anyway, this is beside the point. The point is I'm trying to make is now I have a register map that is a little bit more complicated. So I'm going to keep track of their offsets. And then I have the go and the clear. I could have easily put them here in the upper one, but for the sake of easiness, and I have the data, and I have, like, remember, all these 32 registers are available anyway. So I decided basically to put them here. These are basically write registers, and this one is these are read register, and this one is a write register, and it has a couple of signals. Basically, the go signal tell the timer to go, basically to go and continue and start, and the other one clears it, basically zeroes it out. And you can see, because I have those here, that means I need to pack and unpack these signals. I'm going to provide you with some sort of a mask field, and the go field basically tells me it's 1 at the least significant bit, and the clear field is basically 1 at the second least significant bit, basically where the clear is. And again, as an application developer, what you really care about is, okay, here's the constructor. The constructor doesn't take anything but the core base address, so where it's connected. And really, this is what I care about. So what I care about is the following. I have a function to pause the timer. I have a function to let the timer go or resume, basically to start it. I have a function to clear it. Remember, it's a counter, so clearing it meaning putting zeros in it. And then I can either read the ticks, and reading the ticks meaning reading the value of the counter. The value is stored in these two registers in here. Or I can read it as time, and basically reading time is a little bit different than reading ticks. Reading time involves the system clock, which I already have somewhere stored somewhere, so you can actually convert the ticks to time, and this will be in microseconds. And you're going to see that some of the utility routines later will take this value and convert it to microseconds, for example, or nanoseconds if you choose to. You can actually just read this and build on top of that. And the last function we're going to have is a sleep, and it makes the processor idle for a few microseconds, and these microseconds are passed as a parameter in here. And then as a private member, you're going to see that you have the base address and you have the control, and that control is just basically stores these two values in here. Again, as an application developer, this is all you need. You don't need to know how these are implemented, because you don't understand how the hardware is. You don't understand that you do not need to understand that these are basically counter operations. But if you're developing that driver, and you need to actually understand the implementation of each one of these methods, and you can read these on your own. I'll just pick up one at random. For example, let's pick up the read time, and the read time tells me, okay, you need to read the ticks, okay, which are basically the content of the counter, which is another function in here. You can read it and you can see it. And what you need to do is just divide it by the system clock frequency, which is 100 megahertz, and then you get everything in microsecond, and you just return that value, and that's it. Of course, like if you're curious about how ReadTick operates, you're going to see that I'm doing a couple of IO read, and then I'm just going to assemble them in C, and that's pretty much it. Okay, read the other functions. They're really not that difficult. You can see like each one of them is a few lines of code. Like the sleep just basically goes into a loop that does nothing till that it's basically just doing nothing in here for a certain period of time that I actually specify.